In this video, we will learn how to separate mixtures using filtration and crystallization. We will also learn how to decide which apparatus we need and which method should be used. In experimental chemistry, being able to purify and separate different substances is a key skill. Two useful methods in this area are filtration and crystallization. Let's look more closely at what each of these methods can achieve. Filtration, for example, is useful for separating a solid from a liquid. A good example where we use filtration in everyday life could be how to get coffee grounds from a cup of coffee. On the other hand, crystallization is useful for getting a solid out of solution. An example of this which you may have come across is getting copper sulfate crystals from a copper sulfate solution. While at first glance it may seem like actually these two are doing the same thing, i.e. getting a solid and liquid to come apart, there are actually some key differences. For example, in filtration, the solid which we are separating is insoluble in the liquid we are separating it from, just like coffee grounds and water. However, in crystallization, we have a solid which is soluble in the liquid which we are trying to separate it from. And this is an important difference. Let's begin by taking a closer look at how we carry out filtration. When it comes to filtration, there are two main methods. These are gravity filtration and vacuum filtration. Gravity filtration is quite a lot slower than vacuum filtration. However, gravity filtration tends to be better than vacuum when it's the liquid which is the part that you want to keep. Moreover, gravity filtration is good when you have a large volume of liquid which you need to filter. Vacuum filtration is faster than gravity filtration, and it's also better for filtering small amounts of solid or filtering small amounts of liquid. It's not as good as gravity filtration if you have a lot of solid or a lot of liquid to get through. Don't forget that you can also perform gravity filtration as a hot filtration. This is useful if, while filtering, you get crystallization occurring inside the filter funnel. So let's have a look at how gravity filtration works. In order to carry out gravity filtration, you're going to need an Erlenmeyer, sometimes called a conical flask, and a funnel. In order to make sure that nothing gets knocked over, you should secure your funnel with a clamp or a ring stand. Notice that the conical or Erlenmeyer flask doesn't need clamping because the positioning of the funnel will hold it securely. When you need to remove the Erlenmeyer flask, you simply loosen the clamp on the stand and slide the funnel up the pole. This then gives you the space to take out or put in a conical or Erlenmeyer flask. Don't forget that your clamped glassware should always overhang the heavy base on the retort stand. This prevents anything from toppling over. The last piece of equipment we're going to need is a filter paper. Filter papers are circular and come in lots of different sizes. They're very much like the same filters you'd use to make filtered coffee. In order to get this circular filter paper inside our funnel, we need to fold it. We could fold it into quarters, which would then give us a cone. However, using this method, there would be a part of our cone which has a double layer of filter paper. Having two layers of filter paper for our solution to get through is going to make our filtration even slower. And remember that gravity filtration is slower than vacuum filtration already. So while we could use this method, it's not the most effective. Instead, what we do is we flute the filter paper. This means folding it into lots of small triangles and then alternating which direction these go in so it concertinas up. While this can be more fiddly to do, it means that when we filter whatever it is, it only has to go through one layer of filter paper regardless of where it is. With practice, this will become much easier. Once we've fluted our filter paper, we can sit it inside our funnel and begin our filtration. So our first step is always to set up our apparatus. The next thing we'll want to do is to swirl the mixture that we're going to filter. This means that any particulates at the bottom of our mixture can be thoroughly mixed throughout the liquid. This is especially important if it's the particulate matter that we want to collect. If you don't swirl it, some of that matter might remain in the conical or Erlenmeyer flask and not pass through your filter paper. This then makes it a tricky job to get out of the flask. Next, we can pour our swirled mixture into our fluted filter paper. You should do this slowly and gradually, swirling again if needed. Be careful not to overfill the funnel. You don't want any of that mixture creeping over the edge of your filter paper and passing down into the flask. This would mean that some of your solid isn't caught and you'd have to do this all over again. If it gets full, let it drain and then add a bit more. What should happen is that the solid particles will remain on the filter paper and your liquid will continue through into the flask. This means we have successfully separated a solid from a liquid. So if this is how gravity filtration works, how is it different in vacuum filtration? Let's begin looking at vacuum filtration by setting up our apparatus. We're going to need a flask which looks a little bit like an Erlenmeyer flask, but it has a glass arm attached. This arm is where we can attach a tube to our vacuum line. Remember that vacuum tubing should be thick-walled, not to be confused with the thin-walled tubing you would use for water or gas. The next piece of apparatus we'll need is a vacuum seal. This is usually a round rubber ring which sits on the top of our flask and will hold our funnel in place. It helps to create a seal all the way around. Next, we'll need our funnel. But this is not a glass conical-shaped funnel like we used in the gravity filtration. This one is more cylindrical and usually made of ceramic. If you look at the funnel from the top down, you'll see that it has lots of small holes in the ceramic bottom. This type of funnel is called a Buchner funnel. And the flask with the sidearm which we are using is called a Buchner flask. Just like with gravity filtration, our apparatus should be attached to a stand to keep it secure. This time we'll secure it to the retort stand with a clamp around the neck of the Buchner flask. Be careful not to over-tighten this as you don't want to damage the glass of the flask. It's important to make sure all of this is secure before applying your vacuum. If it's not secure and you turn on the vacuum, it could pull everything over. Next, we're going to need a filter paper. When you put the filter paper inside your Buchner funnel, it should cover all the holes. If any of the holes are showing, the filter paper you've chosen is too small, so you should change it for a larger one. Equally, if your filter paper is too large, it will crinkle and fold. This means that you could get some of your mixture slipping down through the funnel without going through the paper. This means some of the solid could escape through and you'll have to do this all over again. Make sure that you pick the filter paper which is just the right size. Once our apparatus is all set up, we can begin filtering. First, we can turn on the vacuum to our Buchner flask. Next, before we actually begin filtering, we need to test our vacuum seal. To do this, wet your filter paper with just a small amount of solvent. Try to choose the same solvent that's going to be in your mixture that you're going to filter. So if you're filtering sand out of water, you should use water to wet your paper. If you're filtering some kind of solid out of ethanol, you should use ethanol to wet your paper. Once the paper is wet, if the vacuum seal is good, you should hear a sucking noise. Equally, if you gently try to move your Buchner funnel, you should feel that it's gripped tightly by the vacuum. This means you have a good seal. If you don't have a good seal, now's the time to try to solve the problem. It could be you just need to jiggle the funnel around in the vacuum seal, or maybe your seal is damaged and you need to replace it. Either way, it's important to get a good seal before starting to filter. Just like in gravity filtration, you should swirl your mixture to make sure that you have a good mix of the particulates and they're not all stuck to the bottom of your vessel. You can then gently and slowly pour this mixture into your Buchner funnel. The vacuum should quickly suck the liquid through into the flask with a satisfying bubbling and gurgling. Any solid particulates should be left on the filter paper in your Buchner funnel. If at any point your filter paper starts to wrinkle or come away, stop pouring. Make sure that your filter paper stays flat at all times. This stops any solid slipping through into your flask. If your filter paper gets covered in a thick layer of solid, it can decrease the amount of vacuum you have and block the paper up. To fix this, you may have to pause your filtration. You could gently try to move some of the solid, but that risks tearing the filter paper. So if you do try that method, you must be very careful. If there's no liquid in your Buchner funnel, it might be easier just to change your soiled filter paper for a new one. You also need to keep an eye on the level of the liquid in your Buchner flask. If your Buchner flask gets quite full, it needs to be changed out. If the liquid reaches the height of the glass arm, you're going to suck liquid into your vacuum line, which is really bad. This is why vacuum filtration is best for filtering mixtures which only have a small amount of solid or a small amount of liquid. Now that we've separated insoluble solids from liquids, let's look at separating soluble solids from liquids. To achieve this, we use crystallization. To carry out crystallization, we're going to need an evaporating basin, which is held over a heat source, for example, a Bunsen burner. We place our solution inside the evaporating basin and turn on the heat. As we begin heating our solution, the solvent begins to evaporate off. As we evaporate more and more solvent, think about what happens to the concentration of our original solution. With less solvent, our solution becomes more and more saturated until it's supersaturated. If we were to then turn off the heat, our solution would cool down, and you would notice that crystals would start to form. This is because, as our solution cools down, it's not able to hold quite so much solid in solution. This excess solid falls out as crystals. We could then use one of our filtration methods to filter off our solution that remains and keep our lovely new crystals. And this is certainly one method for carrying out crystallization. This method means that if there are any impurities in our solution, they don't also come out as crystals. So you can consider this a purification step. But it's not the only method of crystallization. Another method to obtain crystals from our solution is to simply keep heating it. As we get rid of more and more solvent, less of the solid can remain in solution. So you'll notice that some solid forms on the edges of the evaporating basin. We simply need to keep heating until all of our solvent is gone, leaving behind all of our solid as crystals. The downside to this method of crystallization is that if there were any impurities in your original solution, these will also have come out as crystals, contaminating your lovely solid sample. So a further purification step would be required. This method also produces much smaller crystals than if you only evaporate the majority and then leave it to cool. If you have the time and patience, you can get some really lovely, large, regular crystals from the first method. You may have done this with copper sulfate solution, for example. Let's summarise what we've learnt about filtration and crystallization. Filtration can be used to separate insoluble solids from liquids. For example, sand from water. We can use gravity filtration, which is slow but good for large volumes. This involves an Erlenmeyer flask, funnel and fluted filter paper. Or we could use vacuum filtration, which is quicker but not so good for large volumes or large amounts of solid. Vacuum filtration involves a Buchner flask, Buchner funnel and vacuum line. On the other hand, crystallization is good for separating soluble solids from their solution. For example, getting copper sulfate crystals from copper sulfate solution, or perhaps getting salt crystals from salt water. This technique involves evaporating solvent from your solution to supersaturate it. You can either then cool it to produce large crystals, or continue evaporating all of your solvent to create smaller crystals.